And thanks for the introduction. Yeah, I'll be talking about transfer learning. I'll start off by introducing the problem. I'll spend a little bit of time on introducing the problem. So this is based on very early work with Guillaume Martinet on the non-parametric side of the problem. And that gave us a lot of intuition towards the parametric side of the problem. And much of what I'll be talking about today is work in the last couple of years with Steve Haneke. All right, so transfer learning, just a quick formal setup. Imagine we have label data from a distribution P. And however, from that data, we want to produce a classifier that works well under a different distribution, which I'll call Q. And throughout, I'll let P be so-called the source and Q be the target distribution. So, and we'll be mostly in classification, although the problem of transfer is much more general than just classification. So again, we have data from a distribution. However, we are interested in doing well on a different distribution. So here is a quick case study, which I like to use because Apple series still doesn't quite understand my accent. And so the case study is Apple series voice assistant. It was initially trained on speech from American speakers. And for many years, it just could not understand most non-native American English speakers. In fact, apparently still does not quite understand Scottish accent. And so now you can imagine what it took Apple to take care of this. Essentially, they had to keep acquiring more representative data and retraining their software, which is rather costly. So here at a high level, then the problem of transfer for them would have been to train on the initial American English speakers and somehow be able to transfer information cheaply to related populations. So that's at a high level, the problem of transfer. It's of general relevance. We have this sort of issue in a lot of applications where data is hard to acquire. So you acquire data from a particular population, but the data is not fully representative of the actual target population. So AI in judicial systems is a huge issue at the moment. Data is acquired often on people already in the judicial system. However, it has to give risk assessment on essentially everyone. You have these type of problems in medicine, in genomics, in IoT. And again, the whole issue is that good data, representative data from the actual target population is hard to acquire. And so industry companies often have to acquire cheaper data that is not fully representative of the target population. So that's at a high level, the problem of transfer. It's been around for a long time. At least people have recognized the problem for the last 15 years. There has been tons of heuristics developed for the problem. However, the theoretical side is still catching up to these heuristics. So interestingly, a lot of basic questions remain unanswered. And it's basic questions that practitioners would care about. So again, suppose that H hat is a classifier that is trained on source data P and is to be transferred cheaply to a target distribution Q. A first question that one might ask is there enough information? Is there sufficient information in the source P about the target Q? And in fact, what do we even mean by information, right? If not, how much target data would suffice? How little of the target data would suffice if we employ, quote unquote, an optimal transfer procedure? Would unlabeled data help? Here, the question, the reason I'm asking the question here is that one of the things that practitioners have done a lot is try to acquire much cheaper unlabeled target data. and hope that the unlabeled target data would actually help somehow. So that question is there: would unlabeled target data work, and to what extent? So here is a different question. And the question is just that given that the different sources of data cost different amounts, is there a notion of optimality, of optimal sampling with respect to the cost of the data, given a particular classification error we want to achieve, right? Is there such a thing? Because if such a notion of optimality of sampling with respect to cost is there, then companies might be able to reduce cost dramatically. So I hope these questions are clear, and these are the type of questions that sort of, when we started working on this a few years back, we were a bit surprised that we don't have complete answers for these questions. So all of these questions just boil down to a very basic question, which is, what is the relative statistical value of data from P and data from Q, labeled or unlabeled? Okay, so what is the relative value? And of course, this will depend on, quote unquote, how far P is from Q. So it will depend on some notion of distance between the two distributions. So that will be the first thing that we'll focus on, is what should the right notion of distance between distributions be? And hope that once we sort of identify the right way to formalize the relation between the two distributions, we are able to start addressing these questions up here. All right, so how are we going to proceed formally? Like I said earlier, I'm going to focus in this talk on VC classes. So the parametric side of classification. So I hope that most people know what a VC class is. Essentially, VC just serves to control the complexity of the hypothesis class. The hypothesis class here can be viewed simply as the set of algorithms, for instance, neural networks, trees, nearest neighbors, and such, the set of algorithms that we are caring about. And we hope that this set of algorithms has bounded capacity somehow. So that will be VC classes. The way we're going to look at the problem is the following. We are going to assume that we have both data, labeled data from P and labeled data from the target Q. And then given a certain amount of labeled data, let's say NP labeled data from P and Q labeled data from Q, given a certain amount of data from both distributions, we want to understand what is the best possible error achievable in terms of these data sizes, NP and NQ. And the way we measure error is just classification error, but excess classification error over the best possible classifier in the class. I hope that is clear so far, and please interrupt me anytime, especially around now, since I'm setting up the problem. All right. So again, we want to understand which notion of distance between distributions between P and Q would capture such excess risk. Okay, so there are many competing notions of distance between distributions that have been tried. Essentially, you can imagine that any notion of divergence, discrepancy between distributions has been tried in the theoretical literature on the subject. So I can go over everything. So I'll just go over the main directions that people have looked at. So there are extensions of total variation. So here, the cartoon I'm putting here is the cartoon I'm gonna sort of work through to explain things. So imagine again, here we have this cartoon with source distribution and target distribution. The difference between the source and the target is simply that we have a lot more of this particular object in the target, of the triangles in the target, and less in the source. And what these various notions of total variation, extensions thereof, which have been tried, essentially do the following. They just consider the difference between P and Q over regions of space. And the regions of space that they look at will be defined by the set of classifiers that are being looked at. So rather than, as in total variation, looking at all measurable subsets of the space, if we looking at linear classification, we'll just look at half spaces. We just look at the difference over half spaces. So many such notions have been proposed. And the type of error they get is the following. So they get an excess error on a classifier, so on various classifiers that have been proposed. They get an excess error that is of the form OP of 1. So something that goes to 0 with sample size, usually with just source sample size, plus the distance between distributions. So this already was something that caught our attention, because it seems to suggest that the best we can do is drive the excess error not down to 0, but down to the distance between distributions. While we can come up with various situations where it seems to us that we should be able to drive the excess error down to 0, even if P and Q are different from each other under total variation type distances. And I'll give examples of that in a minute. All right, another line of work is essentially density ratios and various divergences that are based on density ratios. So Rayleigh divergence, KL-divergence and such. These ratios have been considered, and often it will be norms, particular norms of the radon-Nikodym derivative between Q and P. And if those norms are bounded, properly bounded, then you can expect transfer to happen. The type of error you can get, the type of bound on target error that you can get from this work is, again, OP of 1 plus an estimation error for this density ratio. So essentially, this line of work tends to try to estimate the density ratio and use that for important sampling of some sort. All right, again, we have this question that comes up right away, which is, it seems that the only thing we can do is drop the error down to the hardness of estimating these density ratios. However, we'll see again that estimating these density ratios can actually turn out to be much more complicated than transfer itself. So in that sense, these are not really capturing the hardness of transfer either. And I hope so far that when I write epsilon Q, people now see what I mean by epsilon Q. It's the actual excess error under the target. Q again is the target, P is the source throughout. All right, so like I said, many notions have been tried, nearly every notion up to the most popular notions today, Wasserstein distance and such, MMD. And I'll argue in what follows that much of these notions tend to be slightly over-pessimistic about transfer, about what's achievable on the transfer. Namely, under these notions, we will have situations where P is far from Q. However, transfer is easy. So what essentially has been shown so far is that if under these notions, P is close to Q, then transfer is easy. However, it's unclear that P far from Q implies that transfer is hard. And it turns out that that's not the case under these various notions. And that's what I'll argue now. Okay. Again, here is a source distribution, the same cartoon, and here's the target distribution. We can create large total variation. So the various notions that have been proposed are called a divergence, Y discrepancy. These are the extensions of total variation that I explained a second ago. And we can force these distances to be close to 1/2 in this simple example here, just by looking, for instance, at these areas where the two distributions differ quite a bit, right? However, transfer should be easy in this cartoon, in this simple case here, because if I'm thinking of linear classification, if I put a linear classifier through here, it will work just fairly well on the target distribution. If I'm looking at, let's say, nearest neighbors, again, you can convince yourself that nearest neighbors would work really well, will work fairly well between these two distributions, even though the total variations or notions that are based on total variations can be pushed to 1/2. Again, let me go back for a second. Why 1/2? Because if we look here at this type of rate, it will tell us the rate essentially saturates at 1/2, which would imply that there is no transfer, right? All right. Here is another example that I'm just going to use to explain that metrics are probably inappropriate at transfer, at capturing the hardness of transfer, metrics between distributions. So here, in this example, we have P has very good coverage of the entire space. P, the source, has very good coverage of the entire space, and hence can transfer information to the target, which just covers a subset of the space. And you can convince yourself that it's much easier to transfer from P to Q than to transfer from Q to P. Again, because Q here does not give a good coverage of the decision boundary under P, right? So in that sense, transfer is an asymmetric problem, and hence cannot be captured really that well by symmetric notions of distance between distributions. Here is another example where in this example, I'm letting the target sit on a lower dimensional subspace, right? So that divergences and density ratios will just blow up to infinity. Again, under these cases, it's nearly impossible to estimate these things. First of all, they are not well defined. And yet, again, transfer should be easy. If I put a linear classifier through here, that same linear classifier will work well on both source and target. I hope these sort of examples are clear, right? And so, so we sort of need a notion that captures these various cases and is small under these various cases. So this is a notion that we recently proposed, Steve Haneke and I. Like I was saying, it's a notion that the intuition for the notion actually came out of earlier work with Guillaume Martinet. And the notion is as follows. So we're going to use the following intuition. We'll say that transfer should be easy from P to Q. Somehow, if a classifier has low error on the P, it implies that it has relatively low error on the Q. Okay, so the error of the classifier on the P gives us some information on the error of the classifier on the Q, under the target Q. So we'll try to sort of parameterize this intuition. So for much of the talk, I'm going to make this simplifying assumption that the best H star P, the best classifier under the source, is the same as the best classifier under the target. It just simplifies things, and I will remove that assumption at the end of the talk, towards the end of the talk. All right, so again, the intuition is low error on the P implies low error on the Q. 1 second, let me see how I'm doing on time. And so we just parameterize it through what we call a transfer exponent. Rho, this quantity rho greater than 0. So that quantity is just parameterizing the relationship between excess error on the Q and excess error on the P. It's just saying that if a classifier H has low excess error on the P, it must have low excess error on the Q, and how low depends on this parameter rho. Okay, I hope that's sort of clear. And it's a parameterization of the problem. Rho equal to infinity sort of always hold. But we're hoping for a non-infinite row. And what we'll see later is that rho will capture a continuum of easy to hard transfer. Small rho would imply easy transfer, and very large rho would imply much harder transfer. All right. So let me give some examples of some intuition about this, some additional intuition about this rho, so through examples. So because the excess error itself is involving both y and x, right? I'm just going to simplify the problem a bit further for this, just for the sake of these examples, and assume that y is deterministic. Y is given by y is given as h star of x, and this allows us to reduce the excess error between h and h star, the excess error to just the marginal, the mass of where they disagree, where h and h star disagree. Okay, and so so that rho is simply capturing the relationship between the two marginals. All right, so let's just keep that in mind, that rho right now, under this additional assumption, which is just made here, is capturing just the relationship between the two marginals. And we can now go through these simple examples. So here I'm looking at the classifiers are just thresholds on the line. The entire space is this line. Fp is the density on the P. Fq is the density on the Q. And the densities just differ. The densities, the mass given to these regions, so where HT and H star disagree, the mass given to these regions, the relative mass given to this region is easy to assess, and you can quickly convince yourself that rho will be 1. Okay, the assumption allows us to absorb the constant difference in the densities. So here rho is just 1. However, we can make this example such that the divergence, y discrepancy, so essentially the notions that are based on extensions of total variation can be pushed to 1/4, or even actually arbitrarily to 1/2, while maintaining rho equal to 1, small rho. Okay, I hope that's clear for now. All right. So here again is another example, but back to the example where the target is sitting on a manifold. We are looking at linear classifiers. And again, we can force rho to be very small, 1, but let KL-divergence, Rényi divergence, all that blow up by just looking again at the mass given to this region on the Q and the mass given to this region on the P, and the relative mass. For larger rho, here is an example that to give a sense of larger rho all the way up to infinity. So for larger rho, in this example, I'm letting Q be essentially uniform on the space. Q is the target, essentially uniform. And P is giving very little mass to the decision boundary H star. And the less mass it gives to the decision boundary, the higher rho is. Okay, and if I let FP behave polynomially, you can say exactly what rho is in these cases. Okay, just to give an example of higher rhos, and I'm hoping that sort of captures intuition that if the source gives very little mass to the decision boundary, then it's probably making it harder to transfer to the target. Okay. Now, I talked earlier about the asymmetry of transfer. And so here is another case where we see the asymmetry. So all I just did now is switch which one is the target and which one is the source. Okay. So now the target is giving little mass to the decision boundary, and the source is giving uniform mass to the whole space. Then all of a sudden, we get into a very interesting case here. which we just call super transfer, this is a case where rho is less than 1. And it will turn out that if rho is less than 1, we actually do better by using data from the source than data from the target. Okay, just because the source happens to have better coverage of the decision boundary than the target. And again, these type of situations will not be captured by metrics between distributions. All right, so now I'm going to try and formalize the way in which this notion of rho captures performance limits. In fact, minimax rate, very tight performance limits on the transfer. So to set it up, a first thing that I want to point out is that we cannot just think of the difference between the two distributions, but we have to also think about how hard the classification problem itself is, right? So essentially the amount of noise that we're allowing in either P or in Q. So here in this cartoon, what I'm trying to illustrate is that classification, there is a whole continuum of easy to hard classification. And one of the things we will try to do is also to capture that continuum between easy to hard classification. And by easy to hard classification, I just mean vanilla classification, not classification on the transfer, just vanilla classification. So on the vanilla classification, we can see here intuitively that this classification problem is sort of easier than this other classification problem. And the main reason why is actually two ingredients. One is the amount of noise in the label Y, and also how much mass is given to the decision boundary, right? So the amount of noise is essentially the fact that you can have classes fall on either side of the decision boundary, and also how much you can observe the decision boundary within a finite sample. Okay, and one common way to capture this is a so-called Bernstein class condition. Okay, and the Bernstein class condition just tries to relate the marginal of the difference between a classifier and the best classifier, and the excess error between that classifier and the best classifier. And you can imagine that that difference between the two just has to do with the amount of mass in the decision boundary and the noise in the decision boundary. All right, so this beta here will be between 0 and 1. All you have to remember is that in what follows is that beta sort of captures the hardness of the classification problem itself. And it will turn out that the reason why we are introducing this thing is that it will turn out that the best possible transfer procedures, transfer heuristics, have to do with the value of beta, have to do with how hard the classification problem is in itself. And here we're going to make similar noise conditions on the P, so that the Bernstein condition for P is also beta. In the paper itself, we let the Bernstein condition for P and the Bernstein condition for Q be different. But for the sake of simplifying this presentation, I'm just going to assume that they are the same. Okay. All right. So minimax rate of transfer. Again, recall that we are assuming that the classifier has access to label data from P and label data from Q, two data sets that are independent. And we have the following theorem. And the theorem just says that let H hat be any classifier that is trained on both data sets. The minimax rate over the target, over the excess, the minimax rate for the excess risk under the target takes this form. It takes the form NP to the 1 over rho plus NQ to the -1 over 2 minus beta. So a first thing I have to say here is, first forget this part, the NP 1 over rho. NQ to the -1 over 2 minus beta is the classical rate you would obtain for classification under the Bernstein class condition. beta is between 0 and 1. And all this rate is saying is that we go from a rate that is either 1 over n when beta is 1. So when classification is very easy, when we have very low noise, or to a rate 1 over square root n when we allow a lot of noise in classification. Okay, so it just captures a continuum between easy and hard classification. Now, what's being added here is essentially an effective sample size that is contributed by the target, by the source. And that effective sample size contributed by the source is given in terms of this rho, NP1 over rho. The soup over the pairs here, for the pairs, what we for the pairs of distributions, we assume rho is fixed. So we're looking at a class where the class of pairs of distributions with a fixed rho, but for any value of rho, a fixed beta, a fixed NP, a fixed NQ, but for any of those values. So we have tightness under any of those values, any of those admissible values. H could be any finite VC class. I hope this is clear. Right. And so, and one point I was going to make here also is that we looked around the literature and we could not find such minimax rates from before. So, so to be able to capture through a particular notion of discrepancy between distributions, a rate that is tight under various parameters that capture the continuum of easy to hard classification. All right. One of the first things I want to point out again, I want to point out here about this rate, about just this result, is that it's starting to answer some of the questions I laid out in the beginning. So for instance, what is the benefit of unlabeled data? It turns out that the lower bounds here, do not care at all whether we know the marginals completely. So the lower bounds hold even if we know the marginals. So in other words, infinite unlabeled data does not change the rate, that does not change the minimax rate. So in that sense, in the worst case, unlabeled data might not help. So the benefit of labeled Q data, the relative benefit of labeled Q data is given right away by the rates, because it gives us a sharp transition at which all of a sudden the Q data is more beneficial to driving the excess error down than the P data. I hope that is sort of clear. Again, that's part of the questions we set out to answer, which was, okay, what is the relative benefit of source and target data? And especially towards the question of, is it possible to optimize sampling cost, right? And one result that I don't have time to talk about is that, yes, sampling cost could be optimized if you give me functions, if you give me a particular sampling cost of sampling source and cost of sampling target, we can come up with an adaptive procedure that would automatically, without knowing rho, without knowing beta, achieve the optimal sampling cost for certain regimes. And this is all made possible by just first setting up the problem this way and trying to understand what is that relative benefit between source and target samples. All right, if there are no questions here, I'll give some quick, I'll spend a minute on the analysis. All right, so lower bound analysis, I'll just say a few words about it. For those who are used to lower bound analysis, the main issue we just have here is the fact that H hat, our classifier, has to deal with non-identical distributions, samples from non-identical distributions. So it has those samples, but it has to do well just on a single distribution on the target. So that's the main issue in obtaining these lower bounds. So the construction works as follows, just at a high level. So we construct a family of pairs of distributions P and Q, indexed by classifiers in our fixed VC class. So we construct such a family indexed by classifiers, and we ensure that these product distributions, P and P times Q and Q, indexed by H, these for different H and for different HH prime, that these are close in KL divergence, that the product distributions themselves are close in KL divergence. However, that the marginals on the Q are far from each other. So that's the key ingredient in the construction. And the rest of it is particular extensions of Fano's lemma that you can find in Tibakov's non-parametric book and or in earlier work by Baron and Lee. So for the upper bound analysis, here is the thing. So first, it's a basic upper bound is a basic oracle upper bound is easy to obtain. Okay. However, the main thing we are caring about here is adaptivity to rho. So an oracle bound, what I mean by an oracle bound is a bound that knows all the distributional parameters, rho, beta, all those things, right? An algorithm that knows all that can achieve the upper bound easily. However, what we are caring about to be closer to practice is an algorithm that doesn't know that the transfer exponent rho. It does not know the transfer exponent rho, and in general, it's very hard to estimate distance between distributions. And in particular for rho is defined in terms of H star, which is unknown. And hence it's hard to estimate. So hence the question for us, are there algorithms that can achieve this upper bound without knowing rho? So again, it depends on this noise parameter beta. So when beta is equal to 1, it turns out that a very simple and naive algorithm that people use in practice, a naive heuristic that people use in practice, actually is minimax adaptive. I don't know if I'll call it adaptive to rho. Yeah, so it's minimax adaptive to rho. It just do a simple ERM, empirical risk minimization, on combined source and target data. So you throw the source and target data together and you pretend that they are from the same distribution, you do ERM. If beta is 1, beta is 1 correspond to, for those who are familiar with it, correspond to so-called Massard noise condition. So ERM on combined source then does well, is minimax optimal. And the way we show it is just through some non-IID uniform Bernstein bounds and usual fixed point argument that I use in learning theory. So unknown level of noise for any beta. For any beta, it turns out that outside of beta equal to 1, actually, so this is something that we just only showed recently in a new archive, that for if beta is not 1, then this ERM is no longer optimal. It cannot work, right? So for any beta, here is a simple algorithm that is optimal. So the algorithm does the following. So it minimizes R hat Q, it minimizes the empirical risk on the Q, subject to doing well on the data on the P. And how well depends on this delta NP. I'm not giving fully what it is, but delta NP is just a sense of the variance of the error on the P of the given classifier. All right. So so I hope this heuristic is clear. And it's a common heuristic also where you first do well on the P, you try to first do well on the P, but rather than just rejecting every hypothesis, you keep a version space of hypotheses that are still good candidates on the P. So that's what it's doing. It keeps hypotheses that are still good candidates on the P. And then now optimizes over the new data Q. Okay, and so this procedure can be shown to always be nearly minimax optimal up to log terms. Okay, so here I'll do a quick summary of what I just talked about, and then it seems like there is a bit of time to get into some new directions. So here, a quick summary. We came up with this notion rho that sort of captures a more optimistic view of transfer between P and Q, in the sense that in various regimes where other notions of distributions, other notions of distance between distributions are very large, rho remains small, and transfer is actually can be shown to be quite fast. It allows us to start sort of classifying heuristics, the various heuristics, which ones are optimal, which ones are suboptimal with respect to this minimax rate. Cost-sensitive sampling is possible without knowledge of rho. And quickly, I said earlier that I will remove this part where I assumed in much of the talk so far that H star P is equal to H star Q. If the H stars are different, the rate just changes with an addition here. The addition to the parts of the rate that is contributed by P is the excess error of H star P on the Q. We also have to change the definition of rho slightly, because rho was defined with respect to the combined H star earlier. Now we just define rho with respect to H star P only. And then you get again this and then you still get a rate that is in terms of rho, that captures the relative benefit of the two samples, of the source and target samples. All right, so I'll quickly talk in the next 5 minutes about current work that we just put a new paper on archive with Steve Haneke. And so it's trying to extend now this sort of single source transfer to a multi-source transfer. So what we have now is rather than just having a single P, we have multiple Ps, okay? And still a single target Q. So often people call it multi-source. It turns out that multi-source and multitask are not so different. The only multitask usually refers to wanting to do well under every distribution we have. And here we just reduce it to wanting to do well under one distribution. And that's often called multi-source. So the thing that now brought us into this multitask or multi-source problem is the following, is that even though this has been studied for the last 10 years, every single paper we read on this problem has the following sort of a surprising rate. The rate, while you will expect that now you have multiple sources, right? Let's say you have 100 sources. You would sort of expect that the rate of convergence should be in terms of the aggregate sample size. The rate of convergence to the target should be in terms of the aggregate sample size. However, if you look at the worst parts of the upper bounds that are obtained in the literature, it is in terms of a single source. So if I have 100 sources, each with 1,000 data points, the final rate of convergence obtained so far has been in terms of 1,000 rather than 100 times 1,000. So that's essentially what was sort of perplexing to us. And we try to now use the tools that I just described to try and address this question. So what we find is quite rather a bit surprising. So first, the setup now again is big N sources, PT, and each one having transfer exponent rho t. And we're going to look again at the simplest case, which is where all the H stars are the same. So it feels simple enough. All the H stars are the same. The target classifier is the same. And so we should be able to get a rate. It feels like we should be able to get a rate that is in terms of the combined sample size, not in terms of one sample size. Okay. So what we then see is that there is actually a discrepancy between the minimax rates in multitask setting and the adaptive rate in multitask task setting. And I'll explain it in a second. So the minimax rates that we obtain of this form, they combine. So let NT be the sample size from source T. Okay, so they essentially combine the different sample sizes up to some rho bar T being sort of the average transfer exponent between the sample, between the distributions that I included. The key points being made here, without having to spend too much time about the form of the rate, is that the rate, the minimax rate, is truly in terms of a combined sample size, is in terms of an aggregate sample size. However, the moment we start looking at adaptive strategies, this is what we get into. Again, when beta is equal to 1, ERM on combined data does achieve this rate, does achieve achieves the minimax rate. However, as soon as we allow beta greater than beta less than 1, what we get is that a particular greedy strategy that needs access to a little bit of information, and the little bit of information is a ranking between a ranking of the sources to the target. So it's a ranking that, so you need to know which source is closest to the target. And so you just need to know the ranking, but you don't need to know the exact values of rows. So if you have this ranking, but without knowing the exact values of rows, you don't know beta either, you can achieve this rate up to log terms, just with the ranking. Okay, and it's a simple greedy strategy, but which I don't have so much time to describe. But it's an extension of the Lepsky approach I described earlier. Now, soon as you are outside of these two regimes, there exists no adaptive strategy. There exists no adaptive procedure outside of these two regimes, and which was surprising to us. So essentially, what we show is that any procedure without knowledge of the ranking and outside of a ranking and outside of beta equal to 1, any procedure necessarily achieves a worst case rate that is just in terms of the target sample size. The assumption here is that all the procedures at least know which data set came from the target. Okay, if they at least know which data set came from the target, so they can always achieve the best rate in terms of the target sample size, but they cannot achieve better. And even when H star is the same across all the distributions. And all we had to do to show this was to add this, another soup here. And what I mean by that is we just randomize all possible rankings. So the same type of lower bound strategy, but now we look at the class and then we look at a bigger class that just randomizes these classes. And you can then show that you just cannot adapt to any of these classes. So I'll probably stop here. Somehow what I wanted to convey is that one, not only this is a new area, I mean, not so new, the last 10, 15 years of importance to practitioners, but it brings up a lot of neat theoretical questions that we are just only starting to sort of understand. So thank you for having me, and happy to take questions.